Hello, for the GCSE Physics Paper 1, I'm going to go through question 2, and as normal, press pause and play again throughout the video so that you have some extra thinking time, or it will give you a chance as well to have a go at some of the questions before I go through them. So for question 2, a teacher used a Geiger-Müller tube and counter to measure the number of counts in 60 seconds for a radioactive rock. The counter recorded 819 counts in 60 seconds. The background radiation count rate was 0.3 counts per second. Calculate the count rate for the rock. So first of all, what do we mean by count rate? So that just means how much radiation is released every single second. So I'm just going to draw this out. So here is our Geiger-Müller tube and counter, and going into it is some radiation from our rock, but we've also got some background radiation adding to it as well. And we know that there's 819 counts in 60 seconds, and we also know that the background radiation gives us 0.3 counts per second. So our task is to find the count rate for the rock. So we need to find whatever this is per second, take away whatever this is, and that's going to equal our count rate just for the rock. So if we have 819 counts in 60 seconds, if we do 819 divided by 60 in a calculator, that then equals 13.65. So that means there's 13.65 counts or 13.65 bits of radiation every single second. But that will only get you 2 marks. We need to carry on reading. The background radiation count rate was 0.3 counts per second. So background radiation, that can be caused by lots of things. It could be cosmic rays from the sun, it could be other rocks in the atmosphere, it might be nuclear fallout from a nuclear explosion that's happened many years ago. So all around us there's radiation, and you have to take it into consideration. So it's 13.65 that's being read, but you then need to subtract the 0.3 counts because that's there in addition to what the rock is causing. So the rock is causing 13.65, take away 0.30, so per second the rock is giving 13.35. For question 2.2, a householder is worried about the radiation emitted by the granite worktop in his kitchen. 1 kilogram of granite has an activity of 1,250 becquerels, BQ. The kitchen worktop has a mass of 180 kilograms. Calculate the activity of the kitchen worktop in becquerels. So activity, or measured in becquerels, that just tells us how many nuclei are decaying per second. So very similar to counts per second, how much radiation is being released per second. So in this case, there's 1,250 becquerels being released per second. We know we've got 1 kilogram of granite, and then we need to scale it up to 180. So for each kilogram, it's 1,250 becquerels. So for 180, it's just 180 times 1,250. And that, if you put it into a calculator, is then equal to 225,000 becquerels. Question 2.3. The average total radiation dose per year in the UK is 2.0 millisieverts. Table 1 shows the effects of radiation dose on the human body. So what we can see is 10,000 millisieverts means immediate illness or death within a few weeks, 1,000 radiation sickness but unlikely to cause death, and 100 the lowest dose with evidence of causing cancer. And just look at a pattern just here. So we're going from 10,000 to 1,000 to 100, so we're dividing through by 10. The average radiation dose from the granite worktop is 0.003 millisieverts per day. Explain why the householder should not be concerned about his yearly radiation dose from the granite worktop. And then, just in case you've forgotten, 1 year is 365 days. So per day, it's that amount, and we need to know what it is over 365 days. So in a year, it's going to equal 365 multiplied by the 0.003. Make sure in the calculator you put the right number of noughts, and that gives you an answer of 1.095 millisieverts. Now, What I wouldn't worry about is the unit, millisieverts, because what we just care about is radiation dose. Now, you could be given any number of random units to deal with, but as long as you understand roughly what it means, so a high number is dangerous, a low number of whatever these millisieverts are is not that dangerous, you can then make a comment. So you've calculated how many units or how many millisieverts there are in a year, and then to get the final mark, because it's 2 marks, is to then state something that it's far lower than anything that can cause any serious illness. So for question 2.4, bananas are a source of background radiation. Some people think that the unit of radiation dose should be changed from sieverts to banana equivalent dose. Suggest one reason why the banana equivalent dose may help the public be more aware of radiation risks. So this then leads back to the idea of all these random units that can be used. So let's use another random unit, but one that maybe can be better understood. And the reason it might be better understood is because people can probably imagine a banana. So banana is a type of food, and bananas grow in soil that's radioactive. So they will absorb some of the nutrients from the soil that will be radioactive, and then we as humans will eat them. So we are, in fact, eating radiation when we eat a banana. But as we've just seen, generally speaking, radiation should not be considered a problem, certainly in low doses. So one reason why the banana equivalent dose may help the public be more aware of radiation, so you can then start comparing it a lot easier. So people are able to compare a radiation risk compared to how many bananas that they might eat. So that then brings us to the end of question 2. Any questions, as ever, let me know.